Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join in my channel as a member and support me and my channel. This is my channel. Please subscribe my channel if you have not already subscribed. Thank you. Right. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test July 2025. In this video, we discuss the solution of a problem from the section Real Analysis. And the problem is related to the uniform convergence of sequence of functions. This question is placed in part C, which is a multiple select question. There may be more than one answer and the question carries 4.75 marks. The question ID is 562954140. Further, this question is suitable for all these examinations. The given question is, for each n greater than or equal to 1, let Fn be a function from the set of real numbers to itself defined by Fn of x is equal to e power minus n square x square by n. Which of the following statements are true? We are given four options. Option 1 talks about the sequence Fn converges uniformly to 0 on R, and the sequence Fn prime converges uniformly to 0 on the interval minus m to plus m for some in the open interval minus m to plus m for some positive real number m. Option 2, the sequence Fn converges uniformly to 0 on R, and the sequence Fn prime converges pointwise to 0 on R. Option 3, the sequence Fn converges uniformly to 0 on R, and Fn prime does not converge pointwise to 0 on R. Option 4, the sequence Fn converges pointwise to 0 on R but not uniformly on R. Right. Let's now discuss the solution of the problem in detail. We have the sequence of functions Fn, where n belongs to a set of natural numbers, where Fn is a function from R to R defined by Fn of x is equal to e power minus n square x square by n, where x belongs to R. We first discuss about the pointwise convergence of the sequence Fn. For any fixed x belongs to R, we have e power minus n square x square greater than 0, correct? And e to the power of n square x square greater than or equal to 1. Note down, it's not minus n square x square, it is e power n square x square greater than or equal to 1. If you expand in e power n square x square, 1 plus n square x square plus so on and so forth. So that will give rise to greater than or equal to 1 for any fixed x belongs to R. Agreed? So that is 0 less than e power minus n square x square is less than or equal to 1. It's bounded. Right. So this implies 0 less than or equal to limit n tends to infinity e to the power of minus n square x square by n is less than or equal to limit n tends to infinity 1 by n. You are multiplying throughout by 1 by n and taking the limit. Right. Now, limit n tends to infinity 1 by n is 0 and this is 0 by the, right, this is limit n tends to infinity of e to the power of minus n square x square by n is equal to 0 by squeeze theorem, by sandwich theorem or squeeze theorem. This is 0, this is 0. Right. So, thus, this implies limit n tends to infinity of fnx is 0. And thus, the sequence Fn converges pointwise to f, where f is the limiting function. F of x is equal to 0 for all x belongs to R. Right. Right. So, our conclusion is the sequence Fn converges pointwise to 0 on R. Right. We move to the next slide for the further discussion of uniform convergence. Right. So, we now talk about uniform convergence of the sequence. We have already seen the pointwise convergence. Right. Let Mn be the supremum of mod fnx minus fx, where the supremum is taken over all x belongs to R. F of x is 0 for all x belongs to R. Therefore, supremum of x belongs to R mod of e to the power of minus n square x square by n minus 0. And that is the supremum of e to the power of minus n square x square by n, where the supremum is taken over all x belongs to R and the modulus is taken out because it is always positive. Right. 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 So, we take this for fixed n, we take e to the power of minus n square x square as y. Differentiate once and equate to 0. We get x is equal to 0. So, x is equal to 0 is a critical point and we calculate the second derivative and substitute x is equal to 0 in this. So, y, clearly y double prime 0 is negative because this will vanish. Here it will be minus 2n square, that will give you negative. So y attains maximum at x is equal to 0. And the maximum value is y max is the value of y at 0. The value of y at 0 is 1. E to the power of 0 is 1. So we come back here. So for a fixed n, the function y is equal to e to the power of minus n square x square attains maximum at x is equal to 0 and y max is the value of y at 0, that is 1. Therefore, the supremum of e to the power of minus n square x square is 1. So, therefore, Mn is equal to supremum of x belongs to R of e to the power of minus n square x square by n is 1 by n. And as n tends to infinity, Mn tends to 0. So, uniform convergence is achieved now. Thus, the sequence Fn converges uniformly to 0 on R, to the limiting function. To the limiting function f is the 0 function. Right. We call on option 4. Option 4 says the sequence Fn converges pointwise to 0 on R. Right. Yes, convergence is pointwise to 0 on R, but not uniformly on R. No, it converges uniformly to 0 on R. Therefore, the option 4 is not true. Okay, we move on to the next slide. Right. Now, we consider Fn prime. So far we have seen the sequence Fn converges pointwise to f, where fx is 0 for all x belongs to R. And we have seen that the sequence Fn converges uniformly to the function f, where fx is equal to 0 for all x belongs to R. Now we move on to Fn prime x. So we talk about the pointwise convergence of the sequence Fn prime x. And Fn prime x we have calculated here, and it is minus 2nx into e to the power of minus n square x square. This is Fn prime x. Right. If x is equal to 0, Fn prime 0 is 0 because x is present here. Therefore, limit n tends to infinity of Fn prime 0 is 0. No problem. Right. When x not equal to 0, limit x tends to infinity of Fn prime x is limit n tends to infinity of minus 2nx e to the power of minus n square x square. Fn prime x we have written, and this is minus 2x into limit n tends to infinity of n by e power n square x square. As n tends to infinity, this will be infinity by infinity form, which is a indeterminate form. Use the L'Hopital's rule. Right. For that L'Hopital's rule, it is minus 2x into limit n tends to infinity of the derivative of n with respect to n1 by the derivative of e to the power of n square x square with respect to n. So that is this one, e to the power of n square x square into 2n x square. As n tends to infinity, this will be 0. So this is 0. This is 0. So what it gives? Thus the sequence Fn prime converges pointwise to G, where g of x is 0. This is what we have seen for all x belongs to R. So that is the sequence Fn prime converges pointwise to 0 on R. We call on option 2, wherein it says Fn converges uniformly to 0 on R and Fn prime converges pointwise to 0 on R. Yes, both of them are true. Right. And option 3, Fn converges uniformly to 0 and Fn prime does not converge pointwise to 0 on R, which is false, because Fn prime does not converge pointwise to 0 on R is false. It converges pointwise to 0 on R. Therefore, option 2 is true and option 3 is not true. Right. We move on to the next slide. We discuss the uniform convergence of the sequence Fn prime to 0 on the open interval minus m to plus m for some positive number m. Right. We recall the sufficiency criteria for non-uniform convergence of a sequence of functions. For non-uniform convergence, the sufficient criteria is given here. Suppose that Fn and f are functions on the set A. If there is a sequence xn in E and a number c not equal to 0, such that Fn of xn minus f of xn tends to c as n tends to infinity, then the sequence Fn cannot converge uniformly to the function f on E. This we will apply for Fn prime, for the sequence Fn prime. For any m greater than 0, choose a sequence xn where xn is 1 by n in the open interval minus m to plus m. Yes, this can be done. Minus m to plus m, we can always choose a sequence xn is equal to 1 by n. Agreed. Now, then Fn prime of xn, we are applying the above theorem for the Fn prime of xn minus g of xn. G of x is 0. That is, Fn prime of xn is 1 by n. So go to Fn prime x. Wherever there is x, you substitute 1 by n. Simplify. And this will be minus 2 by e as n tends to infinity. As n tends to infinity, e to the power of minus 1 and n cancels, and this will be minus 2 by e, which is not equal to 0 as n tends to infinity. Right. So there is a C not equal to 0 such that this happens. Therefore, by the above criteria, by the sufficiency for the uniform convergence of Fn prime, by the sufficiency for non-uniform convergence, the sequence Fn prime cannot converge uniformly to G on minus m to plus m and thereby on the whole of R. Let's call on option 1. The sequence Fn converges uniformly to 0 on R. Yes. The sequence Fn prime converges uniformly to 0 on the interval minus m to plus m for some positive real number m. Yes. Both of them are true. Right. So the option 1, I'm sorry. The sequence Fn prime converges uniformly to 0 on the interval minus m to plus m for some positive real number m is not true. By the above criteria, we have seen this sequence Fn prime cannot converge uniformly to 0 on the open interval minus m to plus m and thereby on the whole of R. Therefore, the second part is not true. The uniform convergence is not there for Fn prime on the interval minus m to plus m. Therefore, option 1 is not true. Are you right? Are you sure? Right. So, summarizing all the options, the answer to this question is option 2. That is the detailed discussion of the solution of a problem from the section real analysis which is related to uniform convergence of sequence of functions. Right. In these two sequences, Fn, the sequence Fn and the sequence Fn prime, their derivatives also. So both the sequences were discussed here, and it is definitely an interesting question. I am sure that you understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Yes, this is my channel. Please subscribe my channel if you have not already subscribed. Right. Yes, I will meet all of you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.